Now in this video, what we're going to look at is a system of two springs. Now this is the lecture materials that will be covered within slides 32 to 36, right? So what we're going to look at is a system that look like the one shown here, where we have two springs that are linked together horizontally. And because we have two springs, we have three nodes here, right? 1, 2, and 3. They are linked together by two springs with spring constants K1 and K2. And what happens now, we will give this spring system an external loading, which are written in capital letters. So capital F is the external loading, right? And the corresponding big letter U, right, is the deformation. Is the deformation at the node. And in this case, are all springs connected together. All springs connected together. Right? Now we know that because we need to solve these two springs together, what we got to do is actually break them apart first into two individual elements. Right, so we need to break it down. Break it down to two individual elements. Right, so in this case, we will have node 1 connected to node 2 with little k1, and node 2 is connected to node 3 with spring constant k2. Now this we set up something that we call a free body diagram. So what happens when they are not linked together? They are free as individual part, right? And now we're going to look at what's the loading on these individual elements. Now in this case, we'll put everything as lower letter to indicate the loading and displacements for each element. Now what does that look like? We will say, okay, the force on node 1 is basically exerted from spring 1. So we will say lower letter F on node 1 with bracket 1. That means from spring 1. And we will have a force F2 on spring 1. Similarly, we will have a force F2 from spring 2 and something like an F3 from spring 2. Right? Now, correspondingly, we will also have a displacement at individual nodes. So here we will have U1 from 1. Here we'll have U2 from 1. Here we'll have U2 from spring 2 and U3 from spring 3. Right? And also we need to make sure there's certain relationship that all these forces must satisfy in order for the whole thing to balance. So we have balance of the forces, right? In this case, we will have on node 1, we will have F1, that's the external force. It must balance what? The force on node 1 that is driven by the spring. Right? Similarly, on node 2, we'll have all the forces from the external loading must balance all the external forces from the spring. So that look like such. And similarly, we can draw that for F3. So F3 must balance all the forces from spring 2. Right? So we have the basic finite element set up for these two springs. Now we're going to write down the matrix equations. Write down the matrix equations for each element. Now, because you have individual elements, you can refer back to what we done for an isolated spring, which we covered in the previous video. Now, if you plot that matrix equations, it's basically a mechanical repeat for what we done in the previous video. So spring, I put brackets, spring 1, that gives me a matrix equation look like this: K1 minus K1 minus K1, put up, K1 times U1 on spring 1, U2 on spring 1 equal to the force 1 on 1, the force 2 on 2, right? And similarly, on spring 2, we will have plus, put plus here, K2 minus K2 minus K2 plus K2 times U2 on 2 with U3 on 2 equals F1, F2 on 2, and F3 on 2, right? Okay, now we have two set of equations together. Now, what you're going to notice is that the little u, right, here, no matter whether you look at individual element level or at the whole system level, they should be the same, right? Because the point, no matter, whether you deform for individual spring or together in the global frame, they should be the same. The ruler doesn't change whether you break it down to the individual part or not. So what does that mean? That means I can move or rewrite this little u as the capital U. So U1 goes back here, U2 goes here, U2 goes here, and U3 goes here, right? So now we have two equations, 1 and 2, that link the displacement or the deformation at individual node to the actual force exerted on element, say 1 on spring J. So F, let's write it down, Fi J in this notation is the force exerted on element J at node I, right? So this is what happens when you break down to individual node and individual elements. Now we have two equations, but what you're looking at is the behavior of this whole system, right? We have this system as a whole, but we set up the equations for two systems, right? Now the problem is how we're gonna combine these two systems back to the whole thing. Combine them together, combine. So we want one equation for the whole system. We don't want two equations for two elements, right? So the way to do it in this simplest case is to say, okay, in equation 1, what we are missing? We are missing something about node 3, right? Here we are missing something about node 1, right? So we got to add the equation back here. Now how do we do that? The way to do that is to identify or to know for the final system we have 3 nodes. So we want a 3 by 3 matrix equation, right? And what we are starting with, we started with 2 by 2 matrix equation. And how do we change a 2 by 2 into a 3 by 3 system? So 2 by 2 into a 3 by 3. How do we do that? Basically, we use a trick called zero padding. That means we basically put 0 into missing elements. This mixing matrix element. So if you look at 1, what we want is something called U1, U2, where U3 in this case is 0. We'll put 0 there, equal to F1 of 1, F2 of 2. And in this case, you don't have anything got to do with 3. You put 0 back, and you know that the 2 by 2 matrix go to the upper part of this matrix, so become K1 minus K1 minus K1 and K1, where you have all this term to fill up the whole matrix that are missing. So what we do is we put 0 in all these terms to fill up the equations. So similarly, we can write 0, 0, 0, 0, 0, K2 minus K2 minus K2, K2 times what? 0, U2, U3 equals the 0, F2, 2, and F3, 2. Right? So you have two set of matrix equations that change from 2 by 2 into 3 by 3, and both have, identical. The node, right, occur at the identical position in these two equations. For example, if you look at node 3, they all occur at this position. So both equations have all the information about all three nodes, even though one of the nodes doesn't occur in a specific element, right? Notice that you can combine. Okay, so we are here. We were back at this point where we had two equations. Now we change into 3 by 3 equations, and now we need to combine the two equations together. Now, how do we do that? We basically can do it by adding these two together. So we just add two equations term by term. Right, so this one, adding this one, give you the matrix element for the first matrix element in the final equation, which is K1. Now, if you repeat this, it's minus K1, 0, minus K1, and you look at this one is K1 and K2, so it becomes K1 plus K2 minus K2, 0, minus K2, K2 times. Now, you don't add anything from the actual vector or this eigenvector here. They kept the same, except now you have relating to all the displacement at all three nodes. So that becomes U1, U2, U3 equal to, but the force you got to add it up because each node has the force. If they are linked together, say node 2, they have the force from both springs, so you got to add them up, the force F1, 1, F2, 2, plus F2, 1, and F2, F3, 2. Right? Now you can simplify this force a little bit better because we know that these forces must balance out each other to the external forces as we described above. So what we have here is F1, F2, and F3. So in this case, we have set up the matrix equations for the two spring systems. Okay, so in the next video, we'll look at how we might be able to solve these matrix equations if we are given some boundary conditions.